очень хорошо владею русским языком, поэтому моя презентация будет на английском, но если есть какие-то недопонимания, какие-то вопросы, то я могу ответить либо на русском, либо на английском, но мне легче выражаться на английском. Я работаю биоинформатиком в компании на одном проекте, где я стараюсь помогать ученым и девелоперам общаться между собой так, чтобы из этого не получились ссоры и нецензурные выражения. И проблема в том, что есть большой-большой срыв между тем, что знают девелоперы, и что требуют ученые. И поэтому я хочу попытаться в следующей своей работе как-то помочь немножко приблизить эти два мира. So today essentially I will be talking about statistics and data analysis. And this is important because in the last 10 years there are two buzzwords that became very, very big. So the first one is big data and the second one is data mining. But I will be talking about neither of them. I will talk about the simple, usual, casual statistics because they are at the basis of any kind of further development. So actually, when you think of a statistician, you usually imagine a very, very weird guy who is talking formulas, who's very, very difficult to comprehend, and who can talk to nobody and is doing some very, very secret stuff. Well, actually, this is not the case at all, and I will try to explain a bit what statistics is and what it can bring to you and how you can approach this whole field, how can you learn statistics, starting from what you already know. So, first of all, what is statistics? Statistics is the whole field of mathematics and data analysis that helps turn raw data into knowledge. And nowadays, data is extremely cheap. So you can obtain data from any part of your activity. And knowledge is a bit harder to get. And knowledge actually helps you make observations about your data, see what the data is, what it contains, try to understand whether two types of data sets are completely different or they are similar. In this case, we go into fields known as hypothesis testing. And then, starting from very small observations you have, trying to infer some knowledge about the greater field that lies behind. So this is the type of the field that is called statistic inference. So it's inferring knowledge, going from small knowledge to making general assumptions. Okay, let's think, what are the immediate benefits? If you start reading a book about statistics today, what are the things that you will know by evening? And then I will start with a very simple example. Imagine you're 20 years old, you just graduated the computer science department of your faculty, and a friend comes and tells you, okay, come join our team, we have a great team, and our developers earn on average $1,600 a month. And this is very good for an Eastern European country. And what you imagine, first thing you imagine, okay, so this is the first case. So we have a starting salary at about 900. So if it's a team of 5 people, the person that's exactly in the middle earns the average income, and then at the end is the CTO who has a higher salary. And you say, well, that's an awesome team. But what this expression can actually mean is also the second case, where the entry level is very low, and there is one guy that has all the money because he was the founder of this team, he gets everything, and the guy in the middle does not approach the mean salary. So, because here we have two notions that refer to the term of average, and that can be interpreted differently. So it's the term of median, the one who is in the middle, and it's the term of mean, that is the sum of everything divided by the number of elements. So it depends on what you want to hear and what you want to understand by average and what data has to is told to you. And if you know that this is happening, if you know that this information is partial and incorrect, the first thing you will learn is to ask the right questions. Because average is represented by all these statistics concepts. And each of them can make something appear, and each of them hides some information. And the question you have to to ask, even in this case, is what do you mean by average? They say, well, the average is mean, and then you ask, what do you mean by mean? And they ask you, what do you mean by what do you mean by mean? And it's a little confusing, but you know where to stop, so you found the information. And the other question is this enough? Is it enough to know what is the mean salary, the average salary, the median salary? What else should I look at? What else should I look for? What kind of information is relevant about what expects me in the future? And this is where we go into data analysis. And the first step in data analysis is called exploratory data analysis, and it's the idea of observation. So you take a data set that might be quite big, that you cannot go through one by one, and you do on it some kind of very simple computations by using either quantitative techniques. So these are actually this is some summary information, where you look for graphical techniques, just visualization, that gives you an average idea about what is happening and lets you understand the data that you have and make an assumption about it. Make an assumption about what this data looks like. And in the observation step, aside from these quantitative techniques that are actually implemented by very simple formula, and they exist everywhere, a very important thing is visualization. And I will show you why. This is probably my favorite data set as an example, because here are some points in space, and if you try to make 6 different measurements, if you don't look at this data, and you just say, compute the midpoint on the x-axis, compute the midpoint on the y-axis, try to make a line that passes through all these points, that passes closest to all these points. Show me how distant this data is on x. Show me how dispersed this data is on y. All these things are identical. So all the numbers, 6 parameters, that characterize this data set are identical. But these data sets are completely different. So this is where visualization comes into hand. Because first of all, you take I'd say you take a random sample if your data is too big, and you try to look at it. And you try to estimate whether what you are going to compute further is meaningful. Because here, it makes sense to go by a line, even if this point kind of messes up the thing, because the line should go a bit lower. Here maybe, but that thing is not a line. You could approximate it to a line, but it's not what you want. And this is why looking at data, observing data, making some very general assumption about it is good. But this is not enough, because what is usually done afterwards is the idea of hypothesis testing. So actually you look at your data and you say, I think this data can be approximated by a line. And what you do next is say, how good is the approximation by a line? Is this data truly linear? And is this, for example, is the trend that I think that exists here, is it apparent, or is there some evidence that supports it? For example, if I made an experiment and I want to see some improvement, do the results that I received confirm the expectations? The fact that I wanted to receive some higher values or anything? Are 2 types of data gathered under different conditions similar, even there are some difference, or they're significantly different? Does the system behave differently under various conditions? And this is where we go into the concept of testing a model. And what would you do hypothesis testing? So I'll give you an example, maybe I shouldn't give it to you, but it's a part of how our developers work. So we have some algorithms that generally take, even on the same data set, because they base on randomization, and depending on how the seeds are set, they vary somehow in time. And how we measure time, so it's actually, you start turning your fingers, and it ends, and you say, oh, that was not fast enough, let's optimize it. And then you optimize it, because the whole thing is pretty complex, you don't make any optimizations, and again you turn your fingers and you say, yeah, okay, last time I turned my fingers 6 times, now I turned them 4 times, so this means it's extremely faster. But this is confirmed by nothing, it's just because it happened because you want to believe it. And this is not how you publish a result, and this is not how anybody will be satisfied with what you got unless you prove that this time it was indeed faster. And if, let's say, imagine you have something that is running, the first time you get 1.5 minutes, 2 minutes, and 1 minute, and the second time you get 30 seconds, 1.5 minutes, and 2 minutes. Is the second time really faster? Of course, if you measure the 30 seconds with the 2 minutes in the first case, it is faster. But you have also data that is different. So what do you take? How do you express this? And this is where the concept of hypothesis testing comes in place. And there are, of course, established protocols that allow you to make these comparisons. And the third thing is, in statistics, what is done is inference. I actually know more of inference from the science, from life sciences, but to give examples more adapted maybe to your activity, is something when you are using a tool that is somehow a black box because you delegated some task to something else. And generally, you know how long this thing is taking. You make your request and you're waiting for a response. And you say, okay, I made 10 different requests that are pretty similar. I know the average time that is necessary to receive my response. What should I expect in the future? What should I expect the time to be when I make the future requests? If I am to set some boundaries on it, should I expect it to be between 1 and 100 seconds, or should I expect it to be between 1 and 10 seconds? What are the boundaries in which a big behavior should be located? So this is statistical inference. You make some small measurements and you go outside and you look at the general picture. If you say, I want to learn statistics, you go to Stack Overflow, you go to any of these Stack Exchange, Math Exchange, everywhere, they will say use R, because R is the classical statistics workbench. It's an amazing language. There are lots of people using R. It has a very rich library of already existing solutions. Lots of packages in R. The whole community uses it. And really, these things are great. This is great about R because it's popular. It has lots of tools. And what's bad about R is actually everything else. So R is something that was created by statisticians for statisticians. As a language, it is not very powerful because it's even hardly to say if it is object-oriented or not, and it looks pretty difficult. R is something that is taught by default in most courses, and as I say, it's a big pain in the class because unless you have some very strict recipes you do, once you do have some, let's say, problems of processing data, of getting data into the format that is requested by a certain function that you are trying to use, it's very difficult. So if a solution does not already exist, it is generally difficult to design a new one. And this is why I thought, okay, let's see what could you do in Ruby. Because I'm not going to talk a lot about Ruby. I cannot give bad reviews to you because you'll be dissatisfied with that. But let's say what you all believe is that Ruby is a general purpose programming language. It is flexible, beautiful, elegant, it's intuitive, it's easy to use, and it can manage all the tasks from data collection to processing to presentation. So if you already have a project, everything that starts from collecting the data to doing the analysis, to integrating, to sending the data back to where you need it, can be done in Ruby. And the most important thing is that you already know it, and you already know how to use it, so you won't think of, okay, so I have this function implemented somewhere in R, so this means that I need to add R to my project, which is maybe not something you'd like to do every day. So there are actually two collections of functions that are present in Ruby. So the first one is StatSample, and it contains everything that is done for exploratory data analysis. So you have plotting functionality, you have functionality that allows you to compute some statistics about the numerical vectors, and there are some statistics, some general tests in the part of hypothesis testing that are already implemented. They're pretty good. stat sample is extended and much richer functionalities in the scientific is the whole scientific Ruby, I'll call it package, a collection of functions that will give you much richer control of the data. So if you want to learn statistics, look at these two things and they will guide you through it. However, it will be a difficult approach because when I thought I want to do some modeling and because everybody around me was using Ruby, I will try to do the same, I ran into some problems. And there are some problems. The first problem is documentation. And when I mean that there is a problem with documentation, it's a big problem with documentation because I needed to see how a certain method was implemented. It was in stat sample. I looked at it, the description was something, implements it was the name. I was interested in how quantiles are computed. So it was called the method quantiles and it says computes quantiles. Amazing! And that was it. And then I said, oh, okay, but it's open source, I can look at the source code. And I looked at the source code and I realized this code was written by some Chinese mathematician. Because I couldn't figure anything out of it. And it was difficult. So there is a real there's a need to document things and there's a need to be thorough and to be appealing to the general public if you want the general public to use these statistics tools. The next thing is the almost complete lack of tutorials. So the existing tutorials in statistics, they either take the approach that you're really good and you want to know a lot of the math behind. You're not very good with programming, but you're very good at math and just take math demonstrations, theorems, and so on. The second part of tutorials think that you're completely stupid and they will spend 10 pages explaining what a mean is, and then when you want to do a statistical test, you find nothing about it. And I found nothing. I found almost nothing on statistics with Ruby, but I think here we can learn and write these tutorials ourselves. So you try to learn a subject from somewhere else, implement it in Ruby, and make a Ruby tutorial on it. And here we have a lot to learn from Python because I found some good books, some good publications that take statistics in Python from the general, not the mathematical, theoretical approach, but from the data processing and applied knowledge approach. And there's lots to learn. And the last thing that is really, really painful, and maybe this is why R is still taught in schools, why R is still very popular in scientific publications and in books. There are lots of books written around R. It is the whole concept of literate programming and reproducible research. And what I mean by literate programming is actually the idea that in statistics, it's not as important the methods you are using, but the way you interpret your results. And it's very convenient to have the results and the interpretation in the same context. So it is a bit inconvenient if you write the text somewhere else and you have the script independent from it. You would like to have the description and the script at the same place. And right now it's possible, there are some tools that are doing this for Ruby, but only Markdown is supported, and currently only exports to HTML and PDF is supported, but LaTeX is not supported at all. And LaTeX is currently supported by Python, and it's very good. R works good with LaTeX by two tools that are called knitr and sweep or sweep. And I think it would be really, really nice if we got together and started thinking of something for Ruby as well, because this is what it will bring it to the scientific community, the ability to integrate your results with your analysis and publish everything in one single place. And as I said, the best way to learn something is to contribute. These are projects that are relatively new, that are actively maintained. I think Stat Sample and Scientific Ruby, if I'm not mistaken, were presented at the Google Summer of Code of 2014. So there are still people working on it. There's a need to contribute to it. So please discover it, learn statistics, and contribute to the community. And I think this is pretty much it. If you have any questions.
just use Python.
You know, I didn't ask this question at the previous presentations because it's good to have diversity. It's good to have diversity, and as I said, if it is convenient for you to have a whole project where you need some part of statistics and delegate the statistics to Python, and then come back to Ruby and Rails for your project, you can do this, of course. But I think it introduces unnecessary complexity, and it is really good to develop this part also in Ruby if you want to attract people to come to it. Hey, the question could be why not use Fortran? Why not move on from C?